Hi, this is Professor Stucard, and in this video we're going to be discussing lines and planes in 3 space. So the way we talk about lines and curves in 3 space is actually very similar to and related to parametric equations. So I want to start by kind of reviewing parametric equations first. And we're going to start with the parametric equation in R2, or in 2 space, that only relies on x's and y's and the parameter t. So when we investigate parametric equations, well, a lot of times the best place to start is to make a table of values and then plot those values and see if we can kind of determine what's going on based upon that information. That means the first thing we're going to do is plug in some values for t. We're going to plug in some values for our parameter. And when I plug those values in, I'll get a value for x and I'll get a value for y. And then I'll be able to plot that ordered pair x, y, and it will tell me where that parametric function is for that particular time. In this case, -1. Well, when I plug in -1 for t, well, x, I get -1 plus 1, which is 0. And for y, I get 2 times -1, which is -2. And so at time t equals -1, my function is at the ordered pair 0, 2. And now we're going to do that same process with other values of t. So let's try t equals 0. If I plug in t equals 0, well, the x would be 0 plus 1, which is 1. The y would be 2 times 0, which is 0. And so I get the ordered pair 1, 0. I plot my ordered pair 1, 0, and that's the next place that, again, this set of parametric equations is going to plot to. In this case, for t equals 0. Let's do one last one. If t equals +1, and again, it's that same process. We plug it in. 1 plus 1 is 2. That gives me my x coordinate. And 2 times 1 is 2, which gives me my y coordinate. And so I can finally plot my last point, 2, 2. And I can hopefully clearly see that, well, these points are clearly lined in a line. And so we connect the dots. The one thing I do want to point out is that, just remember, again, when we do parametric equations, the direction matters. And so you got to make sure you put that arrow showing which direction this parametric function is actually moving in the plane, because otherwise we would lose that information. And again, we can put arrows elsewhere on the line too, but we do want to make sure, again, we're taking the time to denote directions. Now, another thing we can do with parametric equations is to reparameterize them. Now, in this case, we can reparameterize this line in terms of just x's and y's. So that means we're no longer going to have the variable t. We're going to try to get rid of the variable t, get rid of that parameter to reparameterize. Now, that doesn't mean we're going to lose a little bit of information. We're going to lose necessarily what direction that function moves throughout time, because again, we're losing that parameter time. But I am actually going to be able to represent this line in terms of just x's and y's. Well, the first thing to do if I want to reparameterize in this case is to isolate t. And in this case, if I look at my equation for x, it's pretty easy. If x equals t plus 1, well, subtract 1 from both sides. T equals x minus 1. And then we're going to substitute what we know for t in now for, well, that equation that involves y. So y equals 2t, but I'm replacing the t with x minus 1. So y equals 2 times the quantity x minus 1, which is obviously, well, 2x minus 2. And again, it's a line in space. And we know just by looking at this and from our other algebra classes that we can define this line in terms of its slope, which in this case is 2, and its y-intercept, which is the ordered pair 0, -2. And we can always define a line using slope and a point, hence, well, point-slope form. Now, before we get to the next concept, we're going to review something from our lesson on vector basics. And remember, when we give vectors, well, the vector notation is always going to correspond to an ordered pair in space if that vector is, well, in standard position situated at the origin. And again, this is something I mentioned. We got to be very careful whether we're using the vector notation with the parentheses or with the triangular parentheses, or an ordered pair is just the parentheses. But again, it's that same kind of idea. So now what I can do is actually take this parametric equation, and instead I can write this as a vector function. So basically we're taking the fact that I have an x component and a y component, and now we're plugging it into my vector notation with, though, an x component and a y component. And now instead of being just numerical, they're actually functions. And so I can, well, create my vector functions in this way. And so, again, notice it's r of t. R is a vector, meaning that, again, my outputs are all vectors. My input is t, my parameter. And again, when I plug it in for my x's and y's, this is what I'm going to get. And if I do the same things that I did before, if I plug in -1, well, that means I'm now getting a vector that points to that ordered pair 0, -2. And so it points to my ordered pair there. Similarly, if I plug in 0, r of 0 points to, well, the ordered pair is 1, 0. And if I plug in r equals r of 1, right, if I plug in 1 for t, well, I end up with that ordered pair. And so my vector function is basically just another way to represent my parametric equations. And we're going to use that idea to really represent almost all of our curves and lines in space. Now, any curve or line in R3, like I said, has got to be given by parametric equations or as a vector function. Any curve or any line has got to be given that way. And again, you're going to see the reason for that is that if we don't do it as a parametric equation or as a vector function, we end up with a surface, because we're going to get any combination of x's, y's, and z's are actually going to relate together in a slightly different way. Something we're going to talk about very soon, actually, when we talk about functions of two variables. But let's not get too far ahead of ourselves. Now, the nice part is, again, there are lots of similarities. If you're comfortable with all the math that's come before, the stuff we're adding on that's new shouldn't be much more difficult. So again, lines we typically write as that y equals mx plus b form, where again we have slope, our variable, and our point. Well, it's going to be very similar when we use our vector functions. So r equals v, then your variable t, and then r0. And again, it's very much going to be related to that point slope. Direction, your variable or parameter, and your point. So let's actually take a look at this. So if I have a line in 3 space, so I have my blue line L in 3 space, well, let's say I have point P0, and that's just some point that lies on that line. That means I also know that there's a vector that's going to point directly to that point P0. And I'm going to call that the corresponding vector R0, or on R0. And so R sub 0 and P sub 0 are very much related. And again, it's that same way where every ordered pair can be given as the endpoint of a vector in standard position. And here's the really cool idea for how we're going to describe our lines. So now that I have my point, I need my direction. And so again, in 2 dimensions in R2, direction is the same thing as slope, but in 3 dimensions it's a little bit different. And again, it's a concept that we are going to investigate much more thoroughly. But for right now, the main idea is that instead of slope, we're going to use a vector to denote the direction of the line. And so the vector v is going to be parallel to the line, which means it's going to basically lie on the line. If I put the tail at p sub 0, then all of my vector v is going to lie on my line. And then now it's just a matter of, well, vector arithmetic. I'm just adding those vectors. R0 plus v, well, gets me to another point on that line. And here's the genius part about this definition. I can scale my vector v by any scalar value, and I'm still going to end up on my line L. For example, if I scale v by 2, right, if I make it twice as big, well, if I'm starting at p0, even if I move twice as far away, I'm still ending on my line. My vector r is still corresponding to a point on my line L. If I were to scale v by a half or make it smaller, again, that resultant vector is still going to correspond to a point on my line L. Even if I make v negative and I go in the other direction, again, it's not going to change the fact that I'm still ending up on my line L, which means that I can plug in any scalar value in front of v, and my result is still going to be on my line. It's still going to be an ordered pair on my line L, which is all a line is. A line is just an infinite set of ordered pairs that follow, or I guess, I'm sorry, in this case, ordered triples that follow a specific pattern. And so, well, that's how we define our lines in 3-space. R, we start at R0, a point we know to be on the line. I can scale it by any scalar t, which is my parameter, as long as I'm scaling it in the direction of v, which we know to be parallel to my line. Now, sometimes we do put r of t to make sure we are being careful to denote what our parameter is, what our actual independent variable is, because again, remember when we're doing parametric equations, your independent variable is your parameter, in this case t. Dependent would be x's and y's and z's type of idea. And again, this is true as long as t is a real number. So again, we define the vector equation or the vector function for lines in 3-space in this way. We have our initial point, our parameter, and that parallel vector telling us direction. And again, remember, parallel vector is your direction, kind of like your slope was in 2 dimensions. So in practice, how would I actually describe the line that connects 2 points, in this case P and Q? Well, let's first find a vector that's parallel to the line. We're going to find that vector v. Because again, to describe a line in any space, we need its direction and a point. And we actually have 2 points already. So I just have to find a vector that's parallel to that line. Well, the easiest way is to find the vector that connects those 2 points. So the vector connecting P and Q, which remember, just subtract their corresponding components. And again, you should be absolutely doing this on your own paper, and working through it together. And if you need to pause the video, please do. And we should end up with the vector that connects P and Q as 1, 0, 2. So that means that the direction of this line, all right, is going to be parallel if we move 1 unit in the x direction, 0 units in the y direction, and 2 units in the z direction. Again, corresponding to my x, y, and z. Well, once I have my direction, then from any point on the line, I'm just going to be able to move by a parallel vector, which, again, can be scaled by any value of t as long as it's a real number. And I should end up with my line. Right? It's that basic formula. So plug it in. So I know 2 points on my line. If I pick the point P, well, there we go. Here's my point P plus t times my direction vector. And that counts as the equation of my line. But notice, I didn't have to pick point P. I could have picked Q, which means that the equation of my line is not necessarily unique. And again, I could have the same exact line in space, and it could be written several different ways. And again, this isn't too unfamiliar. You did this back in like elementary algebra when we had lines in standard form, ax plus by equals c, and we can convert it into slope-intercept form, y equals mx plus b. Same line, but again, its expression is going to look slightly different. Right? It doesn't have to be unique. So your answer might not be the same as somebody else's answer, but it could still be a valid answer for the equation of a line. And so, again, if you're working together on homework or checking answers online, just be very aware of that not every answer is going to match up perfectly, but that doesn't mean that you did something wrong. Right? Again, you check the answers in the back of your book. If it's not the same, that doesn't necessarily mean you made a mistake. It just means that you could have picked a different way to represent it. All right, so we take a look at that vector equation. Well, I can actually do a few things to simplify this. Right? T is a scalar, so I can absolutely distribute that. And then I can actually add these two vectors using, well, vector arithmetic. And if I do all of that, and again, you should write it out, pause the video, and make sure you get to the same point I do. But by performing that basic vector arithmetic, I end up with 5 plus 1t, and again, there's my x component. 3 plus 0t, and again, there's my y component. And then negative 1 plus 2t, which is my z component. And if I wanted to, again, I could separate those by component and simplify. X equals 5 plus t, y equals just 3, and z equals negative 1 plus 2t. And if I separate it out like that, well, these are the parametric equations for the line. The parametric equation for the line and the vector form of the line are actually telling us the same exact information. It's just organized in a slightly different way. And being able to go back and forth between those two ways, or those two methods of representing these lines and curves in 3-space, is going to be very useful for when we have to do calculus related things like derivatives and integrals, so that we can pick the most useful form to make our lives easier. One thing to note is that, again, this is an equation of a line. Every single component is linear. My x component, 5 plus t, my y component, just 3, my z component, negative 1 plus 2t, they're all linear. There's no exponent showing up. And hopefully that should be intuitive to why that makes sense. If my equation is all linear, well, then I have the equation of a line. And that's true for each one of my components. So to kind of recap here, given a line in that r equals r naught plus t times v, where we can define r naught and v, we can write these as vector equations and parametric equations. And again, these are the generalized forms for each of these. Here's kind of that cool thing though. If it's a line, I can solve each of those parametric equations for the same variable t. So for example, if I want to solve for t in my first equation with x, well, I'm going to have to subtract x0 from both sides and then divide by a. Well, subtract by x0, divide by a, and I get t by itself. And I can do the same thing for the other two equations as well. And so I can get t. And this set of equations are known as the symmetric equations because they have to be equal to each other. You're solving for t. The t is going to have to be equal. Now, if you do notice, obviously we are dividing here. And, well, we may be dividing by 0 at some points because we aren't necessarily guaranteed that a, b, and c have to be numbers that are non-zero. It could absolutely be 0. And if that's the case, what that really means is that x equals x naught and y equals y naught. And again, that should kind of make sense because if, for example, b equals 0, well, if I made b equals 0, that's gone away. What's left? Oh, just y equals y naught, and so on. So again, we do have to account for that particular occurrence. But it lets us actually answer more in-depth questions. So for example, where will the line that we just found cross the YZ plane? So in this case, I can use those symmetric equations, and I have to do two things though. First, the YZ plane, if you remember our projections, YZ plane means x equals 0. And we see over here that our y component was just 3, meaning that the b was 0, which means, well, y is just going to be 3. We can't divide there. And we're going to use that information to, well, finish up this problem. So again, plug in a 0 for x right there, and I get, when I simplify that, I get -5. Like I said in the middle, we know that y equals 3, so we can kind of just save that value and almost ignore it. And then when I plug in the values for z minus -1 divided by 2, well, that's z plus 1 over 2. And again, I know that these have got to be equal to each other. So we can solve, multiply by 2, subtract 1. I get my value for z equals -11. And again, work this out on your own. And now we know that the line is going to cross the yz plane at 0, 3, -11. And again, yz plane. So again, we know that x has got to be 0. We also know that for this particular line, my y component is always 3. So there's my 3. And then the last part was to solve for my z component using the symmetric equations. Now, sometimes it's also useful to define just a line segment. So a line segment is a finite piece of a line. Again, typically determined by certain parameters or between 2 points, so it's only part of a line. It does not extend infinitely in both directions. It's very much finite. It has a starting point and an ending point. So that line segment that connects these 2 points would pretty naturally correspond to 2 vectors as well. And so if my points that denote the beginning and the end of my line segment are, let's say, P0 and P1, then I can use R0 and R1 as my vectors that correspond to those points. And again, if I find the difference between 2 points on my line, again, that gives me my direction, V. So again, hopefully that part all makes sense. And now if I take that idea and plug it into my equation of the line, and I replace V with R1 minus R0, well, look what happens here. Well, first, again, I can distribute my t like I did previously. So I have R0 plus t times R1 minus t times R0. And now if I group by r's, so if I group my R0s together, I have R0 minus t times R0. Okay, we can factor here, and I'm going to get 1 minus t times the quantity R0, and then, well, just the t times R1 there at the end. And that's my equation. That gives me a definition for my line segments with parameter t, where t goes between 0 and 1. And so, again, there is my definition for a line segment, or only a part of a line, based on, again, a limited set of values for t. And yeah, this should make sense. I can check this very easily. If I plug in my 2 endpoints, if I plug in 0, if this becomes 0, and this becomes 0. Well, 1 minus 0 is 1, so I just get 1 R0, but 0, yeah, that's going to go away. So if I plug in 0, I get just R0. If I plug in 1, well, again, what's 1 minus 1? 0, so that part will go away. 1 times R1 is R1. So if t equals 1, then I end up at the other endpoint of my line segment. And so again, hopefully everything checks and makes some intuitive sense. Now for some more definitions. Skew lines are lines that never intersect and are not parallel. And I do make a note. Skew lines cannot occur in 2 dimensions. Maybe I should specify 2 Euclidean dimensions. But in 3 space, it actually happens fairly frequently. Skew lines are just 2 lines in space that never intersect. And again, you could hold 2 pencils up in front of your face and easily make sure that they never intersect and they're not parallel. And those are your skew lines. Now let's switch into talking about planes. So we've already talked about planes a little bit back in our previous lessons, particularly about the cross product. And if you remember, the normal vector to a plane is perpendicular to the entire plane itself. And so here's the image we had from our video lecture on cross products. And the idea is that, again, I have my plane in space, and that cross product is actually my normal. So again, that's really my normal vector, not my cross product. And in this case, I want to only consider one other vector in the plane. So instead of A and B, let's switch it to just V. So I have a plane which has vector v lying on the plane, and the normal vector n, and the point where they intersect is going to be P0. All right, and so again, P0 corresponds to some ordered pair x0, y0, z0, and it's some point on the plane. And we're going to pick any other point that lies on the plane. So this is completely generalized, so a point x, y, z. And it could be any point on the plane. And we're going to specifically define our vector v to be the vector that connects points P0 to point P. Which, again, just means we're subtracting the endpoint from the initial point to define vector v. All right, so that's the image we're looking at. Well, now for the mathematics. Now, we know from the dot product theorem that if two vectors are orthogonal, which in this case the normal vector and any vector on the plane must be orthogonal, if they're orthogonal, then the dot product must equal 0. And so, if we let the normal vector be given by a, b, c, and we define vector v like we just did a second ago, then I can absolutely take the dot product of these two vectors. And so, remember, dot product is just corresponding components. So multiply a times the quantity x minus x0, b times the quantity y minus y0, c times the quantity z minus z0, and it's all going to equal 0. And there's our scalar equation for the plane. A times the quantity x minus x0 plus b times y minus y0, that quantity, plus c times the quantity z minus z0 equals 0. There's my scalar equation for the plane. Now the thing is, we can always simplify this to what's called the linear equation for the plane. Because remember, the x0, y0, and z0, again, it's just a point. All right, it's at some point. So they're going to have some numerical values. A, B, and C are also numerical values. And so when we distribute, well, we're going to be able to distribute and combine and always simplify our plane into this form, where again, x, y, and z are the variables, and your normal vector is that A, B, C. And so again, notice that your normal vector corresponds to the coefficients for the x, y, and z in the equation of our plane. So let's do an example. I want to find the linear equation of the plane given my point on the plane, 1, 5, negative 3, and a normal vector of 2, 4, negative 9. Well, there's my equation for the plane that I'm going to use, and it's just a matter of plugging in all the values into the right spots. So again, pause the video, do this on your own, and then check to make sure we get the same answers. But again, essentially, I'm plugging in 1 for x0, 5 for y0, negative 3 for z0, and then I'm plugging in my a, b, and c as 2, 4, negative 9. All right, and now I'm going to start doing the problem. So again, pause, work it out on your own, and then let's see if we get the same answer at the end. So again, plugging everything in looks like this. And so distributing the 2, we get 2x minus 2, 4y minus 20, minus 9z, minus 23. And again, just be really careful with the signs. There's 1, 2, 3 minus signs. Go slowly, be careful, and take your time. And then the last step is, well, I have these constants. I have minus 2, minus 20, and minus 27. I can absolutely combine those together, and boom. There is my equation of this plane. 2x plus 4y minus 9z equals 49. And again, notice how the coefficients 2, 4, and negative 9 match up from my normal vector. You can also get the constant to the other side, and sometimes that's useful too. And so we could add 49 to both sides, and both of these answers are acceptable. So planes and normals. So to find the equation of any plane, you actually need the normal vector and a point on that plane. Now, if you don't know the normal vector, well, we use the cross product of two vectors we know to lie on the plane. And that's actually an example we did in the last video. Now, if we don't have two vectors that lie on the plane, we can use 3 points on the plane to determine those vectors. And actually, that was the example we did in the last video. And so we can actually use the information about the normal to actually compare information about two planes as well. All right, if two planes are parallel, their normal vectors must also be parallel. And if you think about that and close your eyes and try to imagine it real quick, well, yeah, that should make sense. If the planes are parallel, their normal vectors are parallel. And we can actually extend that idea further. And you can actually determine the angle between any two planes by applying the dot product theorem to their normal vectors, because the angle between the planes is going to be related to the angle between the normal vectors. And again, try to draw it out. Imagine it in your head. Make sure you're convinced of that fact before we move on. And the last idea from this section is distances. To determine the distance from any point in space and a plane given in, well, that normal formula, it's just basically applying this particular formula. And it has to do with applying the dot product theorem and evaluating components. You can absolutely look up more details in your textbook if you want to know how that's derived. But otherwise, this is the last piece of information for this section in 12.5 on lines and planes. If you have any questions, as always, please email me. Otherwise, good luck studying. Bye.